It's a pleasure to introduce Professor Shivaram. He is a chaired associate professor at IIT Bombay, and he recently won our research awards from IIT Bombay. And he was earlier working with Yahoo Research, and also a graduate of Texas at Austin. Yes. And one of the things which attracts me is that he is on the board, which is going to say what would be the impact of AI for the next 100 years. So I think really from quarter to 100 years is a long jump, and it is good such as a way in which he can see what he is looking for.
Don't get your expectations up very high. The program is for 100 years, but we wrote the report only for 5 years. All right, good. So it's my pleasure to be here. I think the one thing Professor Shamsundar didn't mention, incidentally, in my first job after graduating, reported to Rajiv. Okay, that's the other connection that exists over here. Okay. Anyway, so while that's happening, I'm very happy to be here, of course. And I think Rajiv really has done me a favor by setting the context for what I wanted to say. Right? Clearly now is a, Now is a time of plenty for AI, right? From the years where it was always something academic and making promises on which it could not deliver, today it is something that is commercially viable. It has implications for society, for economics, right? So for people working in AI, it's definitely a time to celebrate. But that's not what my talk is going to do. We being scientists, I think also have a responsibility to introspect, right? Whether the weather is sunny or rainy. So what I've chosen to do today is to illustrate that there are so many problems in AI. Even when we know how to solve them, we quite don't understand why these solutions work, right? So neural networks and deep learning are a case in point. They work very well empirically on many problems of interest, but they're not very well understood. I'm going to talk more specifically about an algorithm that I've built some familiarity with over the last 3-4 years, which again falls in that category. It's something that works extremely well, but we don't understand why it works so well. So that's really going to be the content of my presentation today. This algorithm is called policy iteration. So it's been around for more than 50 years. Okay, it was introduced in the heyday of operations research in 1960. As I told you, on very, very large MDPs, Markov decision problems, which is what it solves, it'll finish in like 5 iterations, 6 iterations. You won't have to really worry about computational speed. So it's very efficient. It is something that any student who takes my class will do as a programming assignment. If you do a course in reinforcement learning and use the textbook, you'll find it covered there. So it's something that many people use in AI, right? And it is, it's not really like, I don't know, a household term, but it's something that a large section of people doing AI and control theory would associate with. So as if to reiterate that point, I thought I'd illustrate with a Google search. So I imagine many of you in this room will agree that maybe simplex algorithm for linear programming should be a hallmark in terms of how popular an algorithm can be. It's right. It's something that every engineer uses. So if you search on Google for that, you get 26,80,000 hits. Right, if you do the same thing for policy iteration on MDPs, it's not nearly as widely popular, but you still get about 1,86,000 results, right? It's like 4 or 5% as popular, right? If you want to take hits as the measure as simplex for linear programming. So it is something that is used quite widely. And if you argue from the other direction, if you search for me on Google, you're going to get a grand total of 1,120 hits. All right, so I'm bargaining that if you invited me to give this talk today, you're going to get more than your money's worth if I speak about something that's more than 180 times as popular as me. All right, so the talk today is going to be about policy iteration, and just by way of acknowledgement, somewhat coincidentally, this work started not too far away from here. I spent a few months at the Indian Institute of Science, where I collaborated with a couple of people. Neil Dara Mishra, who was there as an Inspire Fellow, is now in IIT Gandhinagar. Aditya Gopalan is still at Indian Institute of Science. And thereafter, I moved to IIT Bombay. So the more recent stuff is work with my students. I'm also working with my colleagues. All right, good. So what's coming your way today? I'll formally define the MDP planning problem, which is the problem that policy iteration solves. And thereafter, give you an overview of this algorithm. It's actually a big family of algorithms. Okay, it's like a strategy. There's multiple ways to instantiate it. And thereafter, tell you a little bit about our own work in recent time about trying to tighten the analysis of policy iteration. And I'm also going to finish with a bunch of open problems. Okay, so maybe it's not a fair assumption that everybody here has a computer science background. So how many people here are from ECS related fields? Okay, it's like maybe 1/3 or 1/4. So I'm going to request that if anybody has questions at any point of time, just raise your hand. I wouldn't mind like taking it then and there. Okay, see, a number of problems of interest, especially when agents are acting in the real world, are ones where actions have long-term implications. Okay, these are sequential decision-making problems. So a robot that's playing soccer, right? The action of passing the ball backwards might be something that is not immediately profitable, but might lead to a state from which a teammate can then take the ball and go and score a goal, right? So it's a good action if you consider the long-term sequence and the result of that. Likewise, with other control problems, if you want to schedule elevators in a building, do you stop for somebody right now or go down, pick up 100 more people and then come up? All right, there's a change of state when you take your action, and you want to go through states that give you an extended series of of high rewards. Rajiv mentioned AlphaGo, right, which was solved 2 years back using reinforcement learning. So at the heart of reinforcement learning also is the sequential decision-making problem. And the most common way to mathematically formulate it is as a Markov decision problem, also known as an MDP. So I'm illustrating it here with an MDP that has 3 states, right, S1, S2, and S3. It's got 2 actions that you can take from each of these states. So from S1, if you take the red action, the meaning of this arrow here is that the probability half, you'll stay put in S1, you'll get an immediate reward of 0. With the remaining probability of half, you will go from S1 to S2, and you'll get a reward of -1. If you take the blue action from S1, it's a deterministic action, all right? This probability is 1. With probability 1, you'll be in S1, you're going to get a reward of +1, okay? So essentially an MDP, to specify it, you have to specify the set of states, the set of actions, the transition probabilities associated with every state and action, and the associated reward, okay? If this is what an MDP is, the question that naturally arises is what do we want to do with an MDP? So the policy, the term policy is a concept that encapsulates the behavior of an agent, okay? So an agent, for example, might choose at S1 to take the action red. Whenever it is at S1, it will take red. At S2, it will again take red. S3, it will take blue. Okay, so this mapping, right, S1 to red, S2 to red, S3 to blue, is called a policy. Okay, and what we would ideally like is a good policy. Good in what sense? In the sense that if you follow that policy, then you will get a high long-term reward in expectation. Not only will you get good one-step rewards, you'll also go to states from which you can get high long-term rewards. So if you want to make that a little bit formal, if we use the term pi to represent policies, then V pi is a function called the value function of pi. So value function takes as input a state. For every state, V pi of S is the expected long-term reward that you will get by starting at S and following pi. Okay, so the first time step reward plus the second time step reward plus the third time step reward, etc. Just to make sure mathematically that we are still doing this in a legitimate way, you tend to discount rewards geometrically. Okay, this is one way of doing it. I mean, if you don't have like a discount which is less than 1, that sum can go to infinity. So formally, we also have to specify this discount factor when we specify an MDP. Okay, so an MDP has a bunch of states, actions, transition probabilities, rewards, and a discount factor. And what we want to find is a policy which basically has a high value function, whatever that means, okay, which from every state gives you high expected long-term rewards. Other questions? Okay, so I've not still told you yet what is the problem we want to solve.
Policy is deterministic for every state. There's a mapping of a single action, or it could be probabilistic.
It could be probabilistic, but it suffices for us to look only at deterministic policies. Yeah, for the purpose of this talk, we'll just look at deterministic ones. Okay, so it turns out that the value function of a policy follows there's a recursive equation that you can write down to to calculate the value. All right, I told you it's expected long-term reward, but you can just do it for one step and then substitute back for the variable. So this is that equation. It's a linear system of equations, and you can solve it. So given a policy, by solving a set of linear equations, which is a simple thing to do, you can find out what is the value function of that policy. So I went ahead and did that for the MDP I showed you on the previous slide. So if we only consider deterministic policies, there are 8 possible policies, red, 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 blue, etc. And 4.45 over here means if you start at S1 and follow the policy red, 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 in expectation, the long-term reward you'll get is 4.45. Okay, and likewise I filled out the other numbers. Now if we look at this table, can we pick one policy as a desirable one as opposed to the others? If you look hard enough, you'll realize that there is this policy here, blue, blue, and red, which is such that for every state, the maximal value that is achievable is achieved by that policy. Okay, so if you take blue, blue, and red, you get 10 from here. You can't get better than 10 following any other policy. Likewise for S2 and likewise for S3. So did we just get lucky, right, that this particular problem had a policy with this property? We didn't. It's a well-known result that given any MDP, the MDP will have an optimal policy. An optimal policy being one that, regardless of state, will have the highest value function. For every other policy, this policy pi star will be such that if you compare it state-wise, it will be at least as high. Okay? So that makes our problem well defined. The MDP planning problem is that of, given an MDP, find an optimal policy for that MDP. There could be multiple optimal policies, but there's guaranteed to be at least one. In fact, there's guaranteed to be a deterministic optimal policy, which is why it suffices for us to look at deterministic policies. Good. So this is the MDP planning problem, and this is the problem that we want to solve. All right. So because this is a sort of theory talk, let me introduce you to some notation. We're going to look at finite MDPs, MDPs which have n states and k actions per state. Okay, if that's the case, then the total number of deterministic policies will be k raised to n. So we will go forward now, and I will tell you about policy iteration, which is a way of finding such an optimal policy. But even before we do that, right, let's take a second to notice that having specified the MDP planning problem, there's already a very brute force naive way of solving it, right, which is what I have done on this small MDP. So what you could do is you could take every possible policy, solve those equations and find out the value function of that policy, put it in a table like this, do a comparison and see which one is the optimal policy, right? Naturally, for doing that, you'll have to look at every policy, which is k to the n time, and for each evaluation, you spend a polynomial amount of time. So this is roughly the sort of bound, the number of arithmetic operations you will need to do that. Yes?
I was wondering that it looks like a theoretic problem in some sense, like a dominating set problem. Is it, because in the dominating set you have, roughly you have almost finite states, right? And then you take a dominating set so that you can find out that what is the kind of, features of the graph that will capture.
So is a dominating set a set of vertices of the graph? Yeah, the difference here is our solution is not states, right, which would be analogous to vertices, but we are looking at policies. So a policy is something that encodes behavior for the entire state action space.
That policy in some sense is a kind of edge connectivity. That is how I will interpret.
Yeah, I'm not that familiar with the problem. Maybe there is a connection. The only difference actually is in general MDPs are stochastic, right? So graphs have like deterministic links. Yeah.
But when you said determinate, I didn't get what you mean by determinate. In some
Deterministic, right?
non-determinacy, right?
No. Yeah, so when you take an action, right, there is non-determinism.
Yeah.
But the policies we are talking about are themselves deterministic, right? So I'm only going to take red from here. You could have probabilistic policies where the agent says with 70% I'll take red, 30% I'll take blue. There's no need to do that. Yeah. All right, good. So, okay, so that is the naive way of doing it. So in order for me to describe policy iteration to you, I just need one more definition. Just like we define the value function as the expected long-term reward starting at every state, there is also something called an action value function, okay, which is just very subtly different. So for a given action A, right, Q pi of A for a given state is the expected long-term reward you will get by taking that action A for the very first time step, and after that you start acting according to pi. Okay, so just one time step you take an action according to A, and thereafter you follow pi. The expected long-term reward you get by doing that will be what is called q pi of s comma a. Again, q is something that you can calculate in polynomial time if you have v. All right, it's just a matrix multiplication and an addition. Okay, good. So now that we have v and q, I can tell you about policy iteration. So what's policy iteration? It's a family of algorithms for finding an optimal policy in an MDP. How does it work? So I'm going to illustrate. So imagine that we are dealing with an MDP that has 8 states, S1 through S8, and 4 actions. The actions are blue, red, green, and black. Okay, you're taking red from S1, blue from S2, etc. Now here's what you'll do. So we are going to look at every state and draw each action either above the line or below the line on the following basis. Okay, the reason we drew blue below the line at S3 is on the basis of the fact that we found out that the Q value of S3 for action blue is no greater than the Q value for the action red. All right, and for a similar reason on the other side, black is drawn above the line at S7 because it has a higher Q value at S7. Okay, so Q is something, given a policy, you can calculate quickly, and we're just using that to decide whether an action must come above the line or below the line. Okay, it turns out that every state that has at least one action that is drawn above the line is called an improvable state. And these actions themselves are called improving actions. Why is that? For the following reason. Let's consider doing the following. Okay, we are given pi. We identify the improvable states of pi. Let us pick any subset of the improvable states, okay, like a non-empty subset. So we pick one improvable state or more of them. We can pick maybe 2 of them or 3 of them here. And in those improvable states, let us switch to an arbitrary improving action. Okay, let's change the action from what we are taking right now to one of the improving actions. So one possible way in which you can do this is as follows. We've decided to improve S1 from red to green, S2 from blue to red. S3 stays put. We've chosen not to improve it. That's fine. I believe S4 and S7 also we've improved. Okay, so you can do this in multiple ways depending on how you exercise your choice. But what's the point of doing this? There's a theorem. All right, it's a well-known result that if you go in this manner from pi to pi prime, then pi prime will be a dominating policy. Now, what do I mean by that? If pi itself does not have any improvable states, you evaluated it and you find everything else has a lower Q value, then pi must be an optimal policy. Okay, that's what this theorem says. If on the other hand it has an improvable state, then surely in one way at least you can improve to pi prime, and it is guaranteed that for every state, pi prime will have a value that's at least as high, and there will be at least one state where pi prime has a strictly better value. Okay, so pi prime is a strictly dominating policy relative to pi. So this is called the policy improvement theorem, and this naturally forms the basis for the algorithm which is policy iteration. So what do? We start with any arbitrary policy. If it has an improvable state, you improve it in some way, go to a new policy, again see if that policy has improvable states, and you keep doing this until you reach an optimal policy. So you're guaranteed to reach an optimal policy because by construction, right, the algorithm can never cycle because you're always going to a dominating policy. You can't come back to the same policy. There's a finite number of policies, and so you will hit an optimal policy at some point. So that's policy iteration. If you want to look at it pictorially, so imagine that this is the set of all policies. Each dot here is a policy. I'm drawing lines between policies if the policy above can be obtained by doing policy improvement to the policy below. So how does the algorithm work? You've started with some arbitrary policy. You do the policy evaluation, the calculation of Q, and you notice that there's this bunch of policies which you can obtain by switching the improvable states. All right, there's multiple ways in which you can do it. You're free to pick any one of them. You do that. Again, look at your improvable states, and you keep doing this until you hit the top. Okay, so this is the policy iteration algorithm. Yeah. Yes, you are guaranteed. Yes. Okay, so clearly there are multiple ways in which you can decide which policies to switch to. Okay, you have a choice. You can go one way or the other, and so different switching strategies will take you through different trajectories of policies themselves to the top. What we are interested in is how long are these paths, right? If you have a particular switching strategy, can you bound the number of steps as a function of the number of states and actions in the MDP, the number of steps to reach the top? All right, so let me introduce you to, I think, 3 different ways of doing it. The most common way of doing policy iteration is to switch every improvable state. Okay, this is the version that was introduced in 1960 by Howard. So this is called Howard's or greedy policy iteration. So if your original policy was this, you improve all 5 improvable states. You still have some choice in deciding which improvable action you'll pick for an improvable state. So you can settle that arbitrarily, okay, any way you want. So that's Howard's. In 1999, Mansoor and Singh introduced a version of policy iteration where you do it randomly. Okay, so if your initial policy looks like this, you might decide to switch only 3 of the 5 improvable states and therefore go to pi prime that looks like this. Or with some probability, you can maybe improve only 1 state, all right? And that's how pi prime will look. Or you can do some other 4 states. With some probability, you'll do all 5 states. So let's not get into exactly the probability distribution over how you do these switches, but that's specified. And this is called randomized policy iteration. Just yet another version of policy iteration is where you switch only 1 state at a time. But if you assume that the states are actually numbered, let's say 1 to n, right? The strategy is you will always pick the, let's say, the rightmost state, which means the state with the highest index. So one improvement at a time, you keep an index and just always do the rightmost. Okay, that's called simple policy iteration. So what have I told you? I've told you policy iteration is a whole family of algorithms. One switching strategy is Howard's, another is randomized, yet another is simple policy iteration.
Is this an NP-hard problem?
No, it's not. It's actually in polynomial time. If you say that the size of your representation is the number of bits you needed to represent the MDP, it's polynomial in that. For the same reason that linear programming is polynomial in the size of the representation. But it's not really polynomial in another sense, into which maybe we'll go into afterwards. Yes? Computationally, they're all like polynomial at every stage. That polynomial itself might be slightly different, but what really we're interested in is the number of steps to reach the top, right? Yeah, so I'll show you that on the next slide. Yeah.
This number of states is actually you are saying polynomial because every time you are improving the policy value. But if you are not, if you look at the graph itself, the graph actually I can have polynomial exponential number of paths
Yeah.
from anywhere I go.
Yeah.
So how is that that exponential number?
No. So what we're interested in is the length of that path.
Yes, that's precisely what
Yeah. No, that's not polynomial.
that's not polynomial.
Yeah, this algorithm is not polynomial in the sense that I was talking to Rajiv. You can also solve the MDP planning problem using other algorithms. For example, you can translate it as a linear program and solve it. If you do that, it will actually be polynomial in the number of bits. But for policy iteration, that guarantee does not hold.
That's exactly what I was thinking, that how can it be polynomial in that sense?
Yeah, it won't. Okay, good. So let me now give you the, yeah.
You started with some random policy.
Arbitrary, yeah. Not random, any policy. Good, okay. So how well do these algorithms do, right? So at each stage, it's a polynomial computation. So what really matters is how many evaluations you need to do before you hit the top, right? So curiously enough, right, I told you the number of policies for a k action n state MDP is k to the n. So in 1999, right, Mansoor and Singh proved that Howard's policy iteration actually takes at most k to the n divided by n iterations. Okay, they improved by a factor of n, like linear factor over the trivial bound, right? Certainly it can't take more than k to the n. They tightened it by a factor of n, and the specific case of k equal to 2 will also show up in our analysis. So that's order 2 to the n over n. Their randomized algorithm, randomization in general helps you do better, to answer Professor Hemachandra. So they show a bound of 1.7 something to the n, and for large action MDPs, it's approximately k over 2 to the n. Okay, so what is really intriguing is when we compare these numbers, these exponential upper bounds with known lower bounds for policy iteration. So to date, right, the tightest lower bound on the number of steps Howard's policy iteration takes on n state 2 action MDPs is only linear in n. Okay, somebody has constructed an MDP and a starting policy and shown that Howard has to look at least n policies before it goes to the top, but we don't have a super linear lower bound even. Right? The upper bound is 2 to the n divided by n, which is like, not only is it exponential, it's just linear over like the trivial bound, right? And the lower is linear. It's also been shown that certain other types of policy iteration, simple policy iteration, for example, has a genuinely exponential lower bound, okay? There's a square root 2 to the n lower bound on how many steps simple policy iteration will take. Okay, so this is the picture as it was until we started working on this problem. So what we have managed to achieve is tighter upper bounds, okay? We have introduced different variants of policy iteration, one called batch switching policy iteration, which we can show on 2 action MDPs takes 1.6 something to the n iterations, and that becomes k to the 0.7 something n for larger action MDPs. We also have randomized variants which can do substantially better. So the bound for k action MDPs is order log k to the n. Okay, we've gone from k over 2 to the n to order log k to the n. All right, these are still exponential bounds, but these are still exponential improvements over the previous bounds. So I don't have the time to tell you about all of these contributions, so I picked just one. So I'll tell you the idea behind this batch switching policy iteration algorithm and how we get this bound. All right, good. So just one result we have to be familiar with. I've already shown you this. This is like the policy improvement theorem. If you only pick improvable states and improve in them, keep the non-improvable states untouched, you'll go to strictly dominating policy. You can imagine doing the opposite. Okay, suppose we only picked non-improvable states and switched in those. We didn't switch any of the improvable states. For example, one example is over here. If you go like that by doing from pi to pi double prime, then it's actually the case that pi will be at least as good. It will dominate pi double prime. Okay, it's just a result in the opposite direction, which I'm going to call policy deprovement. Okay, that's really all we need for me to analyze batch switching policy iteration. So let's take this up as an illustration. So I'd like you to fill in this blank. So suppose we are looking at a 2-state, 2-action MDP. Okay, it's a small MDP with only 2 states. It's got 2 actions. And I ask you, can you bound the number of iterations that Howard's policy iteration will take on such MDPs? What number would you fill it up with? What's the easy way to fill up this blank? So the trivial way to fill up the blank is to just fill it up with the number of policies itself, which is 4, right? 2 to the 2 square. It turns out with a little bit, if we just squint at it harder, we'll be able to show that it shouldn't actually take more than 3 iterations. Okay? So here is my proof. Imagine that the actions here are 0 and 1. It's a 2-action MDP. So, and without loss of generality, assume that your initial policy, the one you pick, is 0, 0. So when you go and evaluate 0, 0, you are going to find either that it has no improvable states, or only the right state was improvable, or only the left state was improvable, or both states was improvable, right? By sort of, these are the 4 possible cases. In the first case, you're already done, okay? There's nothing more to do. The second case, by applying Howard's policy iteration, you'll go from 0, 0 to 0, 1. And again, if we look at how this policy might look, how the states might be improvable, it might be that none of them are improvable, or it could be that the left state is improvable, but it cannot be that the right state is also improvable. It cannot be that 1 is an improvable state when we go from 0, 0 to 0, 1. Now, why is that? Now, that's because had 1 been improvable, then by the policy improvement theorem, you could improve this 0, 1 to 0, 0 itself, right? We'll pick the right state to improve, and by the policy improvement theorem, it must happen that 0, 0 is a policy that dominates 0, 1, right? But 0, 0 is already a policy that's being dominated by 0, 1, and so it cannot be that 1 is an improvable state. All right, so it has to then go to 1, 1, and again in 1, 1, neither of the states can be improvable for the same reason. All right, so in particular, if the, so left can't be improvable because you compare with this. The right can't be improvable. You cannot go from 1, 1 to 1, 0, right? Because 1, 0 is a policy that's already dominated by your original 0, 0 policy because of the way the improvable states looked. can do it in 3 steps or something like that. Yeah.
5 number starting station you have 7th pattern, something like that.
Yeah. Yeah, I think those numbers will be quadratic. These numbers are exponential. Yeah, at least, yeah, they're actually, they look exponential even experimentally when we do it. I'll show you that on the next slide. Good, all right.
So there may be some connection between sorting and this NDP or something like that.
Possibly.
Looks like.
Okay, right. Yeah, so let me just,
Polynomial to exponential.
you'll again stare at a face-off between polynomial and exponential a few slides down the line. So anyway, I've shown you that on 2-state, 2-action MDPs, Howard's only takes 3 iterations. But now I'm converting this idea into an algorithm that works on general n-state MDPs. That algorithm is called batch switching policy iteration. Let's do it on a batch size of 2. So what do I mean by that? Imagine that we have our policy, in this case with 10 states. Now we are going to divide our states into equal sized batches. Okay, so S1 and S2 will be in one batch, S3 and S4 in another batch. So you have like this 5 batches. And our switching strategy is as follows. Given a policy, let's evaluate it. Let's look at which states are improvable. Let us only improve the states in the rightmost batch which has any improvable states. Okay? So what does that mean? If you look at this, then the last batch, S9, S10, has an improvable state. So you leave everything else untouched except S9 and S10. As S9 has to change because it was improvable, S10 doesn't change. When you do that now, you go to pi 2 and again you evaluate. You see that the third batch is the one that is got improvable states, 4th and 5th do not. So you'll only improve these, leave everything else untouched. So you go to pi 3 and likewise you'll keep doing this and you go to pi 4. So this is a policy iteration algorithm, right? It's one way of deciding which states to switch. Now you'll notice by virtue of this construction that if at all you're changing the leftmost batch, right? If you're making any change there, you're only doing that when everything else to the right is non-improvable, okay? So for example, if you're changing, you'll only change pi 4, these 2 states at pi 4 because everything else on the right is already improved. If something else was improvable, you would improve that, right? So you'll have to take a minor leap of faith, but by virtue of the result we saw on the previous slide, it is actually the case that when we look at the trajectory taken by batch switching policy iteration, the leftmost batch can change at most 3 times, okay? Can change like at most 2 times. It can only take one of 3 possible values for very similar reasons, all right? And if that is the case, and the fact that every time you're changing it, everything else to the right is basically solved, it shows up that the total number of iterations you take will follow this recurrence. If you're solving an n-state problem, you're going to take as much time as 3 times, because that's the number of times the first column changes, the time taken by the n minus 2 problem, okay? So if this is your recurrence, then it is solved by saying that the Tn is at most square root of 3 to the n, okay, which is 1.7 something to the n. Naturally, we didn't stop here. Whatever we did with 2-state, 2-action MDPs, you can also do with 3-state MDPs. And by similar argument, you can show that you'll at most take 5 iterations on a 3-state MDP. And the recurrence you'll get by doing that is Tn is 5 times Tn minus 3, which makes it 1.71 to the n. Yeah, so these trees, if you want to know what they're called trajectory bounding trees, because that's what they do. The general principle is, whenever you're looking at a policy and an improvable set of states, by virtue of the policy improvement and deimprovement theorems, there is already a set of policies guaranteed to dominate this policy. That's called the L plus of this policy, and policies that will be dominated by this policy, the L minus of this policy and improvable state. So it cannot be that when you're doing policy iteration, the L plus of a policy that you encounter later is already dominated by the L minus of a policy that is encountered earlier, right? Because there's domination happening with every link. So that's basically the rule that we apply to draw those trees, but you can code this in and you can do it for a larger number of states. We did that, okay? So it turns out that the depth of the trajectory bounding tree for 3, 4, 5 are these numbers over here. If you look at the corresponding recurrences, you'll see that the bound on the number of iterations taken by that version of batch switching policy iteration looks like the last column. Number for n equal to 7 is something we didn't compute, somebody else did. this computation is hard, okay? It's actually like a doubly exponential computation, which is why we were not able to go beyond n equal to 7. All right, good, but the first thing that sort of attracts your attention when you look at this is that it looks like the last column is going down, right? Monotonically, it is decreasing. Is that something we can prove? Is it really true, right, that the last column is proven to decrease as we increase the batch size? We do not know, all right, although we conjecture that that should happen. But what is the implication if that conjecture is true? If that conjecture is true that the last column decreases with batch size, then what's the right batch size to use? The largest, right? The largest batch size is switch all states, right? Have a batch size of n. And if you're doing batch switching policy iteration with a batch size of n, are you doing something else? You're doing Howard's policy iteration, right? You're just switching everything that can be switched. So if this conjecture is true, that the last column is monotonically decreasing, then this number here, right? In fact, numbers that are even smaller than this would be a bound on the complexity of Howard's policy iteration itself. All right, we have very strong belief that this is the case. We don't have a proof. Okay, Howard's been very elusive. We have some numbers, empirical results to back up this hypothesis that a larger batch size is better. So on both small and large MDPs, if you plot the number of iterations as a function of the batch size, you can see that it goes down pretty steeply, saying that larger batch sizes are better. So where does this leave us? Had you stared long enough at the table, you'll probably, some of you might have picked up that those numbers look like the Fibonacci sequence. Okay, so, sorry? Except for the last one, you're right. So, yeah, I can show you again, right? Had this been 34, it would have been exactly Fibonacci, but we have reason to hypothesize that the bound is upper bounded by Fibonacci, okay, that this number should never exceed Fibonacci. That's still a conjecture and a hypothesis, it's not proven. Okay, but is that something we can prove? Okay, that's open problem number one. I have I don't know, 4 or 5 more open problems. We also believe that amongst all deterministic policy iteration algorithms, Howard's is probably the most efficient. All right, although we have these batch switching algorithms for which we have better bounds, we believe that genuinely there is a complexity of each algorithm, right? We feel that that is best for Howard's policy iteration. Again, it's not known. Some of you might be familiar with this thing called smooth analysis, which has been done on in many domains, in particular to analyze the simplex algorithm on linear programs. The basic thesis of which is most linear programs are not easy, right? If you have a hard linear program and you just perturb it by a little bit, you'll be surrounded by a lot of easy linear programs for simplex. Something similar might be happening with policy iteration. I haven't seen a very conclusive proof. Can we also attack it from the lower bound side? Can we do better than linear, right? Even if we do n log n as a lower bound, that's already better than linear as a lower bound. So it is actually known that if you have an MDP that is deterministic, right, where the transitions are not stochastic, they're like deterministic, there are several algorithms that can solve them very easily in polynomial time, all right? We conjecture that Howard's policy iteration also solves those problems in polynomial time. We don't have a proof. And if you want to be really very ambitious, it remains open whether there is a strongly polynomial algorithm for MDP planning. Now, what does that mean? It should not be polynomial in the number of constraints and variables, number of states and actions, and the size of your precision, right? The number of bits you need to represent the coefficients. That's weakly polynomial or non-strongly polynomial. Strongly polynomial would mean polynomial in just the number of states and actions. This I don't know if it's true or not. I'm not conjecturing anything, but the problem is open. Okay, so here are references. The other way to find out more is to just ask me. Let me conclude. So policy iteration is this old, well-studied, elegant family of algorithms. It's got appeal both in theory and in practice when you compare it with other solution strategies. You can also solve MDPs using value iteration, using linear programming, but policy iteration has its merits, which is why people use it. What we have done is sort of scratch the surface a little bit and slightly improve the bounds, but as I've shown you, there is still a vast gap between lower and upper bounds. The analysis techniques are fairly straightforward. What has really been eluding us is to characterize Howard's policy iteration, which is like the oldest form of the algorithm. It seems to be the best, but which is somehow hard to analyze theoretically. This is really what I meant by saying that there are algorithms that we use in AI, but which we are not able to explain, right? That's a case in point. Yeah, so there is a lot of scope for work to characterize this whole area theoretically. And so why did I give this talk in this session, right? There's a class of things that are good in practice. They work well, but they're not very well understood, okay? The point is, AI has a large intersection with that set of things. In a time of plenty, we tend not to focus on such things. We only tend to focus on the work well. But yeah, any algorithm you look at, really like that people use, there is something to understand. What I have done today is illustrate that in the context of one algorithm that I have worked on, which is policy iteration. So let me thank you.
Questions? Yeah. I think you have to speak, anyway you speak at IIT, so why don't you speak loudly?
One simple thing is, can parallelism change any of these complexities? With multi-core and we think it is a process of distributed.
I mean, you're asking theoretically or practically? See, practically, policy iteration is anyway so fast, right? Unless you have like very large state space, I don't see the need to parallelize.
What are the current running times
For what?
in practice for policy iteration to compute?
Yeah, so I mean, I give an assignment in my class with like 100 states and like 10,000 states and 100 actions, right? That will finish in 10 iterations. So it will finish in seconds. If you implement it in Python, 10 seconds. If you implement it in C++, 1 second. Right? So it's really that fast.
So in practice, it doesn't matter. Maybe only theoretically then.
Right. In theory, I don't really know about the complexity that comes from parallelizing. I don't know.
So the analogy to simplex was very well stated. Now in simplex, you find that in the worst case, there could be exponential number of iterations that go along. In fact, we can give specific examples for a specific strategies, as you say, for which it is exponential lower bounded. However, there are something called interior point methods which don't go along the surface but cut across the, assuming it is a 3D volume, you cut across and take shortest gradient to the top. What is that corresponding analogy here? Has it been studied? So you have set of points and you go along the points alone, you reach the top and you're doing the number of iterations study. Is there an interior point analog of that in MDP?
So the interior point analog of that is value iteration, this other algorithm. So policy iteration goes on like discrete points, which are policies. Value iteration goes through value functions, which are real valued sort of entities that,
All right. So in linear programming, the interior point method is indeed efficient. I mean, it's polynomial time. What about value iteration here?
So again, but interior point methods are polynomial in the number of constraints and variables and the size of the linear program, right? If you have like b number of bits to represent your coefficients, that will also show up in the polynomial bound.
I mean, that is the matrix size, so it will be still related polynomially to the number of variables and number of constraints.
Correct. So we can get such bounds for MDP planning. So the kind of analysis that we are interested in here is using a slightly different model called the real RAM model or infinite precision arithmetic. So assume that you can store square root of 2 and pi exactly, right? And you can add, subtract, multiply, divide them exactly. If those are your operations, can you be strongly polynomial in just the number of states and actions?
And what is the answer?
We don't know, right? All these bounds are exponential.
But the conjecture should be yes, right?
No, I'm not brave enough to conjecture about that.
No. For instance,
even for linear programming, that's open, right?
No. For instance, even for problems like integer factorization, which is a famous difficult problem in cryptography, where RSA is based on, there are algorithms which work in polynomial number of arithmetic operations which have this infinite precision.
I see.
And therefore, if you have infinite precision, it's not a small thing. It is a big leap.
Correct.
So the conjecture should be that if you have that big leap, you should be polynomial, but it may be open. That's, I mean, you know better. So it should be open, but there should be a conjecture for it being in P rather than otherwise.
Okay, so we'll put it down as your conjecture. I've not seen any others yet. Yeah, so the other thing, right, the other answer to this question is I don't think enough people are looking at this problem. I mean, it's not like there's a wide literature and I've only given you a subset.
So that is my next question.
Yeah.
So given that you can do an interior point method to solve the problem, what is the need to still subsist with
Yeah, because interior point methods don't give you these strong bounds. right? Assuming from a theoretical point of view, if you're looking at infinite precision arithmetic, suppose I only want bounds that depend on the number of states and actions, that don't depend on the size of the representation.
All right, so there is a ellipsoid method in linear programming
So
which
it's
is
the same thing, right?
not really. I mean, it doesn't use infinite precision, right?
No, it doesn't use, but the bound you will get will depend on the size of the representation. It will be polynomial in the representation, but these bounds, right, don't depend on the size of the representation. Like k to the n times poly kn just depends on the number of states and actions if you're doing infinite precision arithmetic.
Okay, but is it not that once you give the... Sure, sure.
Any other?
Thank you.
Yeah, Chiru.
Thank you.
Okay.
Yeah, Chiranjeev.
Yeah. This is a very nice. First time I think I understood words. Yeah. Many thanks. Excellent. So just have a question on. See, the main thing which you probably brought in is the batch sizes. That kind of analysis is giving you the improvements, right? Now, two questions on that. So, is there a non-unique? So, what batch size should you use? Given a problem, is there a prescription for a batch size to use?
Right. So this table, right, seems to prescribe that a larger batch size is better, right? As you're going from 1 to 2 to 3 to 4 to 5 to 6 to 7, it's getting better and better and better. So is this graph, which plots iterations against batch size. So I would prescribe use the largest batch size and therefore do Howard.
So Howard is the best so far.
Yes.
So all this rest of the things looks immaterial. In that case, if you put it that light, how does the Mansoor, right? Mansoor's random thing, how does it place? Because that's what I want to come to. If Howard is the best,
Yeah.
then
So
it's that 1960, and this is almost 60 years now.
yeah. So from what I can say empirically, Mansoor and Singh, if you compare it with Howard, sometimes one is slightly better, sometimes the other is slightly better. I don't think it depends really on the MDP and the problem, but they are roughly in the same league. So Mansoor and Singh's randomized pulse iteration is also, I would say, is kind of up there. I don't have the graph for it on these, but I would guess that it might more or less be coincident with these red graphs, plus or minus a little bit fluctuation.
But they didn't make this observation that they're better than Howard or something like that.
Their paper doesn't have any experiments. It's a theory paper. All right. Thank you so much. Thanks.
It's a token of appreciation.
Thank you. Thanks.
Thank you.